In 1963, while Arno Penzias and Robert Wilson were studying faint radio signals from the Milky Way galaxy, they found a persistent interference in the microwave region, which was detectable in all directions. Coined the Cosmic Microwave Background Radiation, or CMBR for short, this interference was the first piece of strong evidence for the Big Bang Theory, during a period of skepticism about the origins of our universe. In this video, we will tackle what this source is, and how the strange conditions present in the early universe led to its creation. To do so, we will need to travel back 13.8 billion years to the start of the universe. When it came into existence, the universe was so hot and so dense, and packed into such a small volume, a singularity, that our current understanding of physics is inadequate to describe it. Our best theories break down for timescales smaller than the Planck time, which is about 10 to the minus 43 seconds. We do know that the four fundamental forces, the gravitational, electromagnetic, strong nuclear, and weak nuclear forces, would have been of similar strength at such short distances, and could therefore have been combined into a single unified superforce. After 1 unit of Planck time, the universe had expanded enough that the significantly weaker gravitational force could no longer compete with the others due to the decreasing density of mass, so it became the first of the forces to separate from the rest. Elementary particles began to be created in quantum fluctuations, that is, the spontaneous creation and subsequent annihilation of particle-antiparticle pairs. This created irregularities in an otherwise perfectly smooth universe. As the universe expanded and cooled, it reached the point where it no longer had the energy required to unify the strong force with the weak and electromagnetic forces. As the strong force decoupled from the electro-weak force, it released such a vast amount of energy in such a short time that the universe began to rapidly inflate. In just 10 to the minus 36 seconds, it went from smaller than an electron to the size of a ping-pong ball. Inflation continued until the universe had expanded to 10 to the 35 times its size. It did not stop here. In fact, the universe is still expanding today, but the rate of expansion slowed to a comparatively tame rate after the inflationary epoch had ended. After such rapid inflation, the universe was large enough that the weak nuclear force could no longer compete with the electromagnetic force at this extended range, so the final two forces separated. The rapid formation of quarks and antiquarks began, continually colliding and annihilating one another. They existed as an ocean of free quarks filling the universe, held together by a constant exchange of gluons, in a plasma state called a quark-gluon plasma. A phenomenon known as baryogenesis occurred. For every billion quark-antiquark creations, an extra quark was made, and was left behind as all the other pairs subsequently annihilated. This asymmetry in the quark-antiquark relationship is why our universe consists of matter, not antimatter. Once the universe was cool enough for quarks to slow down, the strong force began to bind them into hadrons, but the baryon asymmetry resulted in the elimination of more antihadrons than hadrons. During this time, leptons dominated the mass of the universe. The universe was still high enough in temperature to produce lepton-antilepton pairs, but once it had cooled sufficiently, this production ceased, and the majority of the pairs annihilated each other. In this era, protons fused to make hydrogen and helium nuclei. Other light elements were also formed in the process. After nuclear fusion ceased due to falling temperatures, the chemical abundances remained nearly constant from here on out. The current universe had the majority of its energy in the form of radiation, photons to be specific, and consisted of a hot, dense plasma of nuclei and electrons. It was still too hot at this point to bind electrons to nuclei. The photons continually interacted with and scattered off of the electrons, protons, and nuclei present in the universe. Nuclei began to capture electrons and form neutral atoms. This was known as recombination, and resulted in a substantial decrease in the frequency of reaction of photons with baryonic matter. This meant that the universe was no longer opaque to photons, it was now transparent, and this was known as the decoupling. These photons were now free to permeate the universe, spreading out in all directions, and, as the universe expanded and greatly cooled, the photons lost energy, so their frequencies decreased. As a result, we presently see this cosmic background radiation as microwaves. The cosmic microwave background radiation was the first piece of empirical evidence for the Big Bang model of the universe. The CMBR can be used to determine properties like the age and composition of our universe, yet it raises new questions that must be answered. There are still ongoing experiments that are trying to gain a higher resolution picture of the CMBR, which would allow for a clearer view of the structures present in the early universe. We are still probing the CMBR to see what other mysteries it might unlock.